All right, so we're going to go deep in immutable collections. People will recognize you guys because you did that excellent interview with Eric Meyer.
Yes.
So real briefly, give a quick overview of immutable collections, and then let's break into it. You guys tell us how it all works. This is going to be going deep.
You start with introduction to immutable.
Okay, so immutable collections, as we're defining it here, are what Wikipedia describes as persistent collections. So they're immutable in the sense that if you have a reference to them, you know that the collection itself will not change at all. There's no guarantee on the items in the collection. That's up to you. And if you actually want to change the collection, you can do so very efficiently by just calling an add method on it. It returns a new instance of the collection that actually shares much of the memory behind, so it's very fast, very memory efficient, easy on the garbage collector.
Great.
Yeah, so before we go into the details, I would like to share one thing. So Wednesday we shipped an update to the immutable collections. I mean, we always ship updates, we always ship betas. That's nothing that's very special. But I think the thing that is quite special is that we received a lot of feedback for immutable collections. Like, people weren't happy with the name. Some people, even suggested to rename it to the persistent data structures. And basically, we did a lot of changes on the API surface area. Like, we tuned it, we extracted types, we moved stuff around. And I think the interesting thing from our perspective is that, I mean, I'm a PM on the BCL team, so we always have this problem. We ship a beta of the .NET framework. Then you have like 36 hours to reply, more or less, right? Because then whenever we get feedback, we take it, but we will typically only fix really critical bugs. We will not really change the design anymore, because betas are pretty close to the RTM date. And if you look back, 4.5 even shipped with a Go Live license, so we already gave people the permission to use it in production, which basically means you cannot make major design changes anymore. But given that Immutable was fairly new, we really wanted to ref the design with our customers and say, this is what we believe is right. Go play around with it. And then we received lots of feedback, and we fine-tuned the result out of it. So I think that's fairly new, that we can actually do major changes.
Excellent. So, I mean, we also discussed last time, I believe, scenarios where this makes sense. I was talking to a .NET developer not long ago, and had asked him about immutable collections. What do you think about it? And his question was, why would I need them? So, let's definitely answer that again, because I know we already talked about it, but since we're here now, I think it's a fair question.
Mm-hmm. Absolutely. So the places where they really shine the most and just screams, hey, I should be using immutable collections, is when you are, one obvious one is the multi-threading scenario. It's the only collection that's really, truly thread safe that doesn't have also a lot of thread safety baggage and overhead. So we do have the concurrent collections in the BCL, which you can use, but they mutate, which may not be what you want. Plus, even if they do exactly what you want, it turns out they actually have a lot of overhead because they're optimized for highly concurrent, not just multi-threaded, where once in a while you might get a hit. But they, from what I understand anyway, correct me if I'm wrong, but if you're only using it from a couple of threads and the interaction is only rare, then you're actually paying a lot of perf overhead and maybe garbage overhead to support that. So the immutable collections are great, and they're very, very lightweight for protecting against multi-threading considerations. And if you've got a lot of places where you have methods that return I-enumerables or I-collections, and what they do internally is do a .to list in order to return a snapshot, that's another place where it screams, hey, you're making a lot of copies, you're paying a perf and a garbage collector hit, and you could avoid that by using these.
Yes, so the one thing that I think is interesting to mention, because I think it got lost last time a bit. I think the interesting thing with thread safety is not so much that you cannot make a single collection thread safe. The problem that you have in complicated system, that eventually when you do this like full scale, you really get to the point where you want to have like snapshot, semantics across your whole state, more or less. In order to implement this efficiently, you need to be able to generate a new snapshot, given some kind of, change delta between the old version and the new version. And this is where immutable collections shine, because they really allow you to, add one more item to the list, and then you get a new instance, but you don't get, all the copying going on. And so you can easily create like really big systems where you have massive state behind the scenes, and you can actually create a new snapshot, but reuse 99% of the previous state.
Right.
Excellent.
You can also do, so as we were developing these and fine-tuning them and tweaking them for the performance that we needed as a Visual Studio product, we were consuming them as we were developing them. You could actually do some really interesting optimizations that you could not do with mutable collections. So, for example, and we'll talk about this more as we talk about the internal data structure, but if you have two lists or two sets, and you're adding one set to the other set, normally that would be, okay, so I have list A and list B, and I want to add list B to list A. You've already defined exactly how it has to work, because list A, you have a reference to it. That same reference has to represent the new collection. And so if list A only has one item in it, and your list B has 1,000, well, now you have to grow list A by 1,000 elements, and you have to, there's no option. With immutable collections, though, if you add 1,000 elements to a one-element collection, internally we figure out, hey, this is stupid. Let's add one item to the 1,000 element collection and return that one. Because semantically it's equivalent. You can't tell that we did that optimization, and yet it's just a whole lot less work for the CPU and for the garbage collector.
Great. So let's break into this.
Yeah.
How did you implement this? Let's look at the insides of an immutable collection.
Okay, well...
The type,
The type.
the object, the
Okay.
class, the
Yeah.
thing that you've created.
So this is originally inspired a lot by Eric Lippert's immutability blog posts. So major props to him. And then we just kind of went on and optimized and enhanced from there.
I mean, to be fair, I think the whole thing is pretty old, right?
Yes.
If you go back to the
That's
60s, you
true.
probably find papers that
Yes.
already discovered
Yes,
it.
this is a
Not
very
that we discovered it,
topic,
like
right?
when we implemented C# or something.
Yes, yes. So what we start with an immutable AVL tree to store. So let's talk about immutable lists, since that's what people are most comfortable with. And it turns out it's actually very similar. We use the same overall data structure for whether it's an immutable list, sorted set, hash dictionary. It's all based on this immutable AVL tree. And so if you imagine, when you create an empty collection, you just have your one node that says I'm empty. And that's because it's immutable, that actually can be shared. Every empty collection uses the same instance. So it's not even one object to represent. It's amortized to 0 objects for an empty collection. Now when you add your first item, this was immutable, so we have to create a new one. So here's your new root node in your AVL tree, and it has, the first item you added. Maybe that's the number 1 in a list event. And so now, what we do have though is a wrapper. We don't expose the internal data structure, obviously, so we can change things in the future. So what we give you is a wrapper instance. So this is your immutable list, say. And this is what we actually give you a reference to. And then it internally has a private reference to the data structure. And when you say immutable list.add 1, what you end up getting, because it of course returns a reference to a new immutable list, well, so now you have a new immutable list wrapper that points to the new root node that has 1 in it. So that's the simplest transition it can go through. When you add a second one, add 2, now your AVL tree begins to get more interesting. Now, list isn't sorted, but it is ordered, so an add is just going to put it at the end, so let's just assume it's going to grow in this fashion. Now, the interesting thing here is 1 was a node, an AVL tree node, so it pointed to null here, right? When you add a second one, we've created a new node which points to null here. So we haven't mutated anything yet. But then 1 actually has to point to the 2 now. So we can't mutate 1 because that would cause previous references to immutable lists to actually change. So we actually recreate 1. So this gets recreated, and then the new immutable list points to that. So again, you get a new reference to a new one. Now, and that you can imagine how that grows. What's interesting though is, let's say now you added, let's go ahead and let's use an insert operation. Are we still on?
Yeah.
Are we still within view? Okay.
We are.
Insert 0, 3. For example. So now what we're saying is we want to add the element 3 into the first position in the list and move everything over so that in the end what you see is 3, 1, 2. That's what we're going for. So now the new tree needs to look like this. 1, 3 on the left, and 2 on the right. Now this is where you start seeing optimizations that we have an opportunity to avoid copying, because if you normally copied an entire list or an array, all these nodes would have to be cloned. But although 1 changes, right, so go back to the change things, 1 changes because now it has a left peer that it has to point to. And 1 is obviously new. So these 2 absolutely change, but 2 didn't change at all. And they don't have back references. So 2 doesn't point to 1, therefore if we change 1, 2 doesn't have to know about it. So we actually point to the existing 2 and to the new 3 and then to the new 1 from our wrapper that we return back to you, and you end up with an immutable list. So we've got maybe a 50% savings in that operation. And then when this tree gets very, very deep, then if, let's say it's 5 deep and you have 1,000 elements in it, then adding 1 element to it, well, we call it a spine rewrite. So let's say you've got all these and it's left, right, and then finally you want to change this particular element. This tree, or this spine, is what you have to reallocate objects for. Everything else, the thousands of elements that are on the left and the right of this one spine, get to be reused. So that's the basic idea, and that works very straightforward with a list. For a sorted set, same thing, we just add equality checks as we go. And instead of the list determining the order, we use comparers to figure out where it goes. Dictionaries, the node's value is obviously effectively a key value pair. One place where it gets a little interesting was, okay, that's fine. If in a list, the ordering is very explicit. The caller decides what the order is going to be.
So that would be my question, like how do you determine the order in which the elements are actually traversed when you ask for the enumerable, for example? Do you just do a depth first traversal, or do you have like something like how do you get the order 3, 1, 2 from this tree, for example?
I guess it would be a depth first traversal, left to right. So
yeah,
that's what we do for the ordered ones. Now, not all the collections are ordered, so the non-sorted dictionaries, we still do the depth first traversal, but the order just isn't guaranteed. It doesn't matter.
Yeah.
Now, so for the sorted collections, obviously we have an order. For lists, we have an order. For queue and stack, but those are the 2 exceptions to this, by the way. Queue and stack do not use the AVL trees. They have no need for it. They're singly linked lists. So, for the hash dictionary and the hash set, however, things got a little more interesting because we need to be able to efficiently find the nodes, but there's no order to those dictionaries. They're not guaranteed to be sortable. We can't just sort it under the covers and pretend, from a public service area point of view, because iComparer, which is the only requirement for these types, doesn't offer an equality check. Just says comparatively these are equivalent for sorting purposes. So, rather, iEquality compare doesn't have a compare check. Rather, I had that switched. But it turns out, since iEquality comparer of T has a get hash code method, which is obviously what we rely on in a hash-based collection, the hash is an integer. Well, we can sort that, actually. So for the hash-based collections dictionary and set, we hash the value, get the integer, and then use the standard tree and say, okay, well, you're storing the value apple.
Yep.
You hash that to the number 513. Well, that is, and then if these nodes are, 1,000, some number here and 800 there and 900 there, and those are all just the hashes of these whatever values they store, then I'll make that larger than this one. Then you can efficiently find predictably whether that item actually exists in the collection and, if applicable, what the value for that key is.
Yeah, I think
Excellent.
before you go into I think you probably want to talk a bit more about what AVL trees are, like what kind of guarantees they give you, why the lookup looks like it does. Because it's a tree, that's fine, but why do we use a tree? Like, what's the awesome part of using a tree?
So let's talk about an obvious alternative. So an immutable list you can just do as an array, right? If you want to make an immutable list of 1,000 elements, you could just have an array with 1,000 elements in it.
Yep.
Then every time you change it, you clone the array. Well, now you have an entire array of 1,000 elements. That's how many bytes? 4 kilobytes at least of memory that you have to reallocate every time you mutate the collection. So that's not very efficient, and you could break that up by saying, okay, well, let's just have array segments of 10 each, and just have a tree of array segments potentially. And in a very, very early version, that's what we did. It turned out that had extremely high construction costs. as you're building this thing up, you're allocating arrays over and over again that get increasing size. The garbage was horrible. So by using a binary tree that has only one element per node, and I know there were some Channel 9 commenters that said, hey, why don't we have a 32 tree or something so that we reduce the proportionality constant in searching this. And that's true, and Roslyn actually has some highly specialized implementations of these collections that do have more values per node, and they do have faster lookup time a little bit as a result. The trade-off that they made, though, and that we weren't willing to make for general purpose collections, was their construction time and the garbage that they produce during construction is much, much worse. On the order of, I think it was to produce a 1,000 element collection or a 1,000,000 element collection or something. They produced 2 megabytes of garbage in the garbage collector, whereas these produced 0. And after all the garbage settled, their collection took like a megabyte of memory, whereas ours took 300K or 220K or something. It was order of magnitudes different. So for general purpose, hey, login is fast enough, look up, this is, and even for them it's login, it's just a smaller proportionality constant. We felt like this was a better trade-off, and the reason, there's those perf concerns also, the spine rewrite is relatively cheap if you only have one value per node, because these nodes themselves are actually very, very small.
So, I mean, why do you make garbage? Like, what's the reason they're making so much garbage? I mean, can you explain a little bit about that?
Yeah, so garbage is when you allocate an object and then you discard the reference to it. And that discarding is effectively an asynchronous operation where the CLR eventually decides, hey, nobody has a reference to this, I can reclaim it and allocate new memory in that same address space. That doesn't happen immediately. The CLR, unlike C++, where you call the delete keyword and now C++ can immediately reuse that heap space, the CLR doesn't do that. And so every time you allocate an object, there's a hidden cost to, hey, eventually this is going to get garbage collected and somebody's going to have to go and discover that that memory is now free, and until then it's going to look like occupied space. Even though you've set the reference to null, that doesn't mean it's garbage collected immediately. So when you're dealing with immutable types and you're making a lot of changes in series, so let's say you were creating this immutable list, and you were calling add 1,000 times. Well, notwithstanding how efficient we've made it, if you're reallocating the spine 1,000 times, then as the list progressively gets larger and you're still making changes, you've allocated 10,000 extra objects, I'm just picking out a number, that no one needs. It's not garbage if someone still needs it, right? The value of this immutable collection is potentially somebody has a reference to an older version, they actually want to keep it. So the fact that you're allocating new objects isn't garbage unless, for example, you're in a method and you're in a loop and you're just iteratively mutating the collection and you've got all of these intermediate states that really nobody cared about and you didn't need to produce copies of all these nodes.
Sure.
So that's where the garbage pressure comes from. Now obviously you do want to be able to efficiently construct and maybe even efficiently bulk mutate these things. And so the next thing that we did, and this is another benefit of using one value per node in this AVL tree as opposed to, say, an array, is these nodes aren't actually themselves immutable. They're freezable instead. And what that allows us to do is when we first create, so let's take this scenario again. So we add the first element. If we know that we're going to add a second element right after this one, then we don't. Let's assume that we have a little green check marks that says that this node is now frozen. We don't freeze this node. So when we add a second one to it, then recursively as we come back out saying, hey, we need to change what you are, it says, well, I'm not frozen. So instead of allocating a new object and returning myself on my way out, I'm going to mutate myself and change the right pointer. And so it comes back out. And so you actually can go ahead and mutate this list all you want, and it never throws away a node. Now, I mean, if you remove a node, then yes, that gets garbage collected. But the idea is you can do all sorts of batch operations on this thing, and it reuses as much memory as it possibly can, even in mutating. Now, this is an immutable collection. Are you saying that it can mutate? No, because those batch so for add and two methods to an add, yes, we're going to mark it as frozen. As soon as the facade class, that little wrapper class that we return, gets returned, we have guaranteed to have checked all of these nodes and say you're now frozen. So anytime you have an immutable list instance or an immutable list instance, it's guaranteed to be immutable. Nothing there will ever change. But if you called immutable list.addRange, for example,
1,000 elements.
exactly. Now we know we don't create the wrapper instance but for each individual step of those 1,000 items. We just call the data structure and say add, and we don't actually call freeze until the 1,000th element has been added. And then we go through, and by then we've got a very deep tree, and none of them have been frozen, or none of the new elements anyway have been frozen. And then we freeze them all at once, and we exit. So you've actually either added 1,000 elements to an empty list, all without producing any garbage at all, or maybe you had an element with 500, or a list with 500 elements in it already, and you added 1,000 more. So the existing nodes were already frozen. If we had to change those, we would have reallocated them, and then they would have been in an unfrozen state while we finished adding. And then finally we say freeze at the end, and we return to you.
Okay.
That's great if you can call add range. Sometimes you can't, whether you're using link or you're in a loop of your own and you haven't discovered all the elements you're adding, but you know you're going to be in a bulk add, but you just can't call one of the bulk methods. That's why we have the builders.
So before we go there, I think let's step for a second, because I think the interesting thing here is that basically we probably need to draw a line here that basically says this is this is basically the public surface area,
Yeah, that's good.
and this is implementation. Right. So basically the trees themselves are also data structures that have add methods conceptually.
Yes.
So basically you can control whether the implementation is something that you already gave away basically. So this is where the flag comes in, right? But it also means that basically a consumer, it's a big difference whether I call add 1,000 times or whether I call add range of 1,000 elements, which is slightly different from, let's say, our current list of T, for example. If you pre-allocate it with 1,000 nodes, then it doesn't matter whether you call add 1,000 times or not. I mean, modulo the cost of method dispatch in general, because basically the data structure doesn't need to grow anymore, right?
Right.
And I think that's different here, right? With immutable collections, it's really important that if you can do it, you need to bulk up most of your operation in order to avoid copying basically, or garbage in that sense. And so the builder is basically trying to give you both, right?
Right. And actually, it's interesting that you brought up if you know up front exactly the list you're going to add, we can construct this even more efficiently. So if you have an empty list, an empty immutable list, and you call .addRange on it and give it 1,000 items, and it has insight into, oh, this is an ordered collection, and I know the size of it. We don't even incrementally build the tree. We can actually pre-map out exactly what the tree is going to look like, and we build it without any mutations at all, not even mutating existing nodes. We just create the nodes from the first place with all the right values, which makes it that much more fast.
Interesting.
And the one advantage that this has over list of T is whether you call add range or add, you tend to have slack space at the end, right? The array will double in size or whatever the algorithm is.
Yep.
And you end up with all the space that you're wasting. So if you're using list of T and you know what size you're going to fill it into, it's a great idea to call the constructor and pass them a capacity.
Yep.
And it grows if naturally. It doesn't throw if you exceed that. But
Yep.
whereas this will never have slack space. So, and I think we mentioned this in the blog. It is kind of a trade-off. It depends on how you use it. So don't count on this, but. List of T has slack space, but because it uses an array, you don't pay the overhead of all the individual nodes. So you win some memory and you lose some memory.
Yeah, which is interesting, right? I mean, you called out in the first blog post basically what the complexity is. So basically, list.add, also you think of being an O of one operation, right? Because you just add one item to an array, which is already there. You just increment, the index that you have, and then you put the element in there. But that is only true when your array, when you still have capacity left, right? As soon as you exceed the capacity, now we have to reallocate this whole thing, copy in the old stuff and then add to it. So technically it's ON,
Right.
depending on what the initial capacity was. Versus in the immutable data structures, basically everything is log n.
Yeah.
I think the only exception is stack and queue, right? Because they're just linked lists, you just add to the end, so there's nothing
Right.
going on.
And it's really important to call out because I think in .NET 1.0 there was this thing that insiders would know where if you did a for each over a list, for each, var, or you didn't have var though, right? You had object. If you did a for each over a mutable list, that actually had some performance characteristic, and people knew but if you do for just an ordinary for loop and index into the list, it's actually faster.
Yep.
Well, that's not true anymore in .NET 2.0 or later, as far as I understand. We fixed that problem, and it's actually the reverse is true now. For each is much better. For list in particular, it might not make any difference, but for some collections, it makes a very substantial difference. And the immutable collections is one very important example of that. Immutable lists indexer. If you had a for loop and you were using the immutable list, every index in, that is not constant time the way list is, that is log n time. So if you're enumerating every single thing like this, now you've got n log n performance, which is not as good as you can get. If you use for each, on the other hand, we allocate one object to hold the stack of where you are in the binary tree so that as you're enumerating through, it really is. You can enumerate the whole list in log n time, or in n time, which is the same as list. You can't enumerate a whole list in anything better than n, obviously. Right? So use for each whenever you can, not just for immutable collections, but for any collection, because you're going to be more likely to get the better performance characteristics you need.
Yeah.
Well, if the loop was vectorized, you could do better than n, right? You could do number of SIMD instructions
If you could do
per loop. I'm just throwing that out there. So you guys aren't auto-vectorized yet.
No, we
the
aren't.
C# people.
Okay, well, there you
All
go.
right, so excellent, man. This is great. Really answering a lot of questions. Just to go briefly to what we learned at the beginning of this, you guys have gotten tremendous amounts of feedback, and you mentioned you made significant changes in your latest release.
Yes.
So as we kind of zoom out now a little bit, let's talk about some of the key changes that you've made. So how does that sound?
Yeah, I think one of the interesting things that we basically had is I think one fundamental difference that Andrew already pointed out was the way you construct those in order to get this guy being a singleton, which can be shared. We really don't want people to call the constructors. So we really said we want to have a factory pattern where you call the create method and then you get something back. The problem with that approach is that, and we already had the exact same issue, and I think it was 3.0, I'm not sure, it might be 4.0 where we introduced tuple. So basically for tuple it's the same thing, right? We have factory methods for tuple. The primary reason for tuple to have factory methods though is not so much that we want to be able to keep singletons around. It was mostly regarding type inference, right? Because the problem is that our types are generic. So you have like you have basically code like this. You have like this. Let's say you have an call it mutable list, and then you pass in basically the type, and then you say create, and then you can say like 1, for example. The problem with that is that basically you have to specify the type because it's a method on a generic type. Now the problem is that sometimes you don't know the type in case of anonymous types. So in order to make that pattern work, we basically did exactly the same thing in tuple, where we basically created non-generic classes. So we have one type called immutable list that's not generic. All it has is basically has the factory methods on them. And then the methods themselves are generic, which basically reverses this a bit. So you don't specify the int here, you actually specify the int over here. And you can say int 1. And that doesn't sound like a big deal, but the interesting thing is that now the compiler is able to infer that type based on the argument you pass in. So you can basically just elide this whole thing altogether. Then the compiler can actually tell you that this is an int. So if you have anonymous types, that basically allows you to use this thing way, way easier. I mean, technically, you could have also used for immutable for anonymous types, but this was kind of weird because you basically had to create immutable list somewhere, and then you could say to immutable, and then you could infer the type. But it was the only case where you could actually do that.
Right.
So I think this was probably the biggest item that lots of people pointed out.
Did you, and one of the other things, of course, have there been any cases of people using it in ways that you didn't intend? Or that they've, you understand?
Somebody was getting clever with value equality and noticed that in the initial release we had value equality in our equals and get hash code methods for these collections.
Yep.
And they noticed, hey, well, if you have a collection of collections, then the value equality doesn't traverse deeply through that tree. Which is why in the second release, we removed value equality, and now they behave more like list of T, where equals is just going to return false unless it's exactly the same reference. And we would like to address value equality in the future. We've had several discussions about that. It's actually a really tough problem to solve in a general way. So in the meantime, you just write your own I equality comparer if that's what you want, or you can just write your own for loop. You can always work around value equality for your specific tree graph.
Yeah, I think we had like hourly length debates how to do that. I mean, it's one of those examples where you think it's a very simple question to ask, like, are you equal to something else? But the problem is it's very hard to define what equality means to you, right? There are various different notions of equality. So one good example would have been like Rosslyn has more or less the same problem when they do the syntax trees in Rosslyn. So they want to compare those, but there are various different things you can compare to them, right? You can say, I don't care about white space at all. So I don't care about comments at all. I don't care about whether it resolves to the same symbols or not. I can say, well, are they just syntactically equivalent versus do they actually resolve to the same symbols as well? And now you have like 500 different options. You can think about how you want to have your equality. And so the way Rosslyn solved is they basically have a specialized equality check. I think they call it is equivalent, and you can specify the kind of equivalence you want to answer. But if you have a very general type in the framework where basically you have a default compare that does something, it's very hard to get a policy that everybody is happy with. And I think we did something very similar for tuples as well, because tuples also have a structure. But the problem with the existing interfaces would have been that they cause boxing, which is like if you have 1,000 elements in a list of int, let's say, now you box 1,000 ints, which goes back to the lots of garbage being produced. And so I think it's not that we don't like value comparisons, it's just that it's very hard to expose it in a meaningful way. So I mean, you can always help yourself by having your own specialized value comparison. It's not super hard to write. I mean, technically we could probably be a bit better if we could actually traverse the underlying trees, but I doubt that it would be like way better. Typically, if you're in your app, you know your policy very well because it's your domain, and so you can get exactly the kind of semantics you want to get. Otherwise, you have to generalize our patterns so much that you can specify everything all the time, and then it becomes this mind-bending exercise of all I wanted to know is whether they are equal or not, and it's not that easy actually to design.
Understood. So let's jump a little bit into the use case again, right? So I mean, multi-threading, concurrency, parallelism. So I'm going to use one of these. I mean, the way that I originally was thinking about this was an atomic collection, or a collection that I can guarantee is not going to change, in the sense that if you have multiple threads trying to update it, I don't have to worry about inconsistency and synchronization issues and stuff like that, which is what you get with atomic things in some sense, right?
Right.
So how are people using this in the real world? The people that you've been working with, the excellent feedback you're getting, what are some cases that they've been using it? So I'm not going to use an immutable list just because I can. So if I'm writing an app where there is no multi-threading going on, and there are a lot of apps that do that, why would I want to use immutable lists? Because I can, or because I want to create this persistent data structure, right? So for the people who are doing concurrent programming that are using this, how's it going? What are the scenarios? How is it scaling? How's the performance? What kind of things are you guys learning from real world usage?
So we have, aside from, we have a lot of experience on that from just consuming inside of Visual Studio, but from the outside, we have heard several people report back saying, hey, I'm switching from concurrent bag to immutable list, and the performance is much, much better. So there are people who were using the concurrent collections we know, and the overhead wasn't justified by how concurrent they weren't or were not. And so we see some uses of people moving from the concurrent collections to these things, and that's great. Again, and you mentioned you have to worry about synchronization and thread safety and stuff. It does depend on what semantics you really need, though. Is it enough that you get a snapshot in time? Because having a consistent collection in the sense that it doesn't get corrupted by multi-threading. That's nice. But if you needed some kind of a guarantee that the value you are looking at is current, then these alone won't get you that. You still need some kind of a synchronization thing. But those types of problems can't really be solved at the framework level. Your application has to decide, what does it mean to have a current copy of a list? The current with respect to what's displayed in the UI, well then you probably need to be on the UI thread and block the data structures from being changed on background threads, etc. Or is it enough that it was current in the last few milliseconds? It's an application-specific decision. You mentioned that you might not use list or immutable list if you're just doing single-threaded programming. And that's true. But another benefit of using immutable objects, even in a single-threaded environment, is because there are no side effects at all, like every operation is a pure operation, exceptions that are thrown out of your method don't leave your application in an undeterminate state. It's very common for programmers to not anticipate all the different exception types that might get thrown and to write adequately tested compensation code in your catch block. So if everything you've been doing inside of a method is pure, which you need immutable types to do, then if the exception is thrown, then ultimately the guy who asked for the operation to be done knows something failed and can display an error message or something and assume that nothing happened. That you're not some, oh, I don't know, am I in a broken state? Do I need to reload now? Do I need to relaunch my app? So that has greatly simplified a lot of VS code where, hey, we don't have to worry about that stuff anymore. And the few mutable, for example, in the project system in Visual Studio, which is perhaps our largest current customer of these immutable collections, that project system has to interact both with these and with the MS Build object model underneath. And the MS Build object model is mutable. And that is actually starting to really cramp our style. If an immutable object model throughout the system would just allow us to be more performant in a lot of cases and certainly handle errors that when the user types an invalid input and eventually an exception is thrown, our code could be much simpler and more reliable if we could be immutable all the way through. And that's even if we're single-threaded.
Absolutely. What about future looking? Like what's on your mind with things that you wish you could get to, you just didn't have time to, kind of things you're working on?
So one thing that we look on right now is basically this very old thing is how do you represent arrays in general? I mean, sometimes you have this thing where you have a data blob, which typically you would represent as a byte array. And typically, if you develop your own systems, you wouldn't have APIs that give you arrays back because arrays are mutable by nature. And so the question is, how do you encode this? Just which type do you use? I mean, I've seen read-only collection of byte, which seems really weird, or Immutable of byte, which is probably the slowest way to represent bytes. And so the very common approach is that people don't expose it as properties; they only expose it as methods. And so that basically, if someone wants to get the data, you always get a copy. So they give you back a byte array, but it's a copy, so you cannot mutate state. The problem with that approach is that if you build larger systems, is you copy a lot. And within VS, probably where you have lots of extensions, they're all done by Microsoft. They form this holistic thing called VS, but they all technically siblings in a large system. So you never trust the other guy, right? And so you always copy because you don't know, and then the same piece of information gets from to the whole thing in a not in a good way. So for raw data, typically your problem is not, oh, I want to get a new version of this array where this one element has a different value. The only thing you really care about is that this whole thing never ever changes. And so one thing that we do consider is having a type called immutable array, which would be very similar to immutable list in the sense that you can index it, you can run over it. The only difference is it wouldn't have these persistent characteristics. So you wouldn't be able to derive a new value. The only way you can construct one of those is you call a factory method, pass in your array, and then internally this method would create a copy once. And then you have one immutable thing you can pass it on in your system, and since no one can leak the reference ever to the underlying array, you're safe forever. And then this thing could be incredibly cheap. It could be just a struct wrapping an array. And I think this is something that Roston, for example, has as well, because they have these big, massive systems. They don't use it for byte arrays, but they have very compact data structures, and so the array is hard to beat in terms of compactness, right? It's contiguous memory, like this is as compact as you can possibly be, and so adding this, is something that we entertain as a very interesting thing that we never had before.
Excellent. And of course, just so people know in the audience, you've used the word Roslyn several times today. That's the compiler as a service project.
Yes.
And we need to go actually talk to those guys. I have no idea what they're up to. Last time I talked to them was TechEd Europe of last year, one of their lead developers. And so apparently they're making a lot of progress because we keep talking about them. And it's great that they're an adopter of your technology. So clearly they use it in that scenario. You need it.
It's cool from several perspectives. I mean, we recently did the API review for Roslyn, so we asked them about questions about the APIs and said, well, the language doesn't really allow us to express that, and we said, well, you own the language, right? It's convenient. So they're now also starting, implementing their own compiler in C# and VB, which I think is really awesome too.
It may be worth mentioning if people use reflection. In managed code, you can do anything you want, right?
Yep.
So immutable collections, for example, they guarantee immutability insofar as people don't use reflection to cheat the system. But one thing that is certainly there, protection, I mean, people do downcasting. Oh, the cast succeeded, now I can turn this IEnumerable into a list and I can mutate it, right? And you can say, well, you shouldn't have downcasted, but the language and the runtime permits it and it's not considered illegal. We do protect against the downcasting case. These facade references, all the references we hand out, they can't be cast to some magical mutable interface. So short of reflection and absolutely going for private members and breaking the rules, they are immutable. Another one-off technology in .NET is from MSR is this concept of language support for immutability, where you say this type is going to be immutable and it's verifiable and you can compile against it and have a lot more assurances. How does this work with that? At the moment, it doesn't. I mean, we haven't tried it. We haven't worked with it to make it work. So if it works, then they did a great job on their end. But for example, the things that concern me about the interaction of those two technologies is, for example, we say it's immutable, and it is, but internally it's not immutable. It's freezable. From a language guarantee perspective, if they, depending on how they do their work, they might say, no, you can't say this is immutable because it's actually a freezable characteristic. And yet, we know that it is immutable, in fact. So how is that going to work together when you bring those two technologies together? We don't know yet, but that's some interesting areas to.
But I mean, the difference there is that this is technology coming from the BCL team.
Yes, it's a library solution to the problem.
This is a library solution that people are actually all going to have their hands on, where the MSR, those guys are trying to push the boundaries and understand things. You really shouldn't ship with their code.
Right.
I would hope.
Yeah. And because we've shipped this, when they say, hey, we're done, we've got this new solution, they're going to have to work with situations like this, because we're not the only ones who do this.
Well, and maybe you guys could partner, maybe, help them do something that works. Maybe they can teach you a few things that might solve some problems. I mean, that's typical things that we do with MSR in general.
Yep.
Those folks are rather intelligent.
Yes.
So, as we are, I mean, as the product teams are as well, I just mean that there could be some interesting, I'm not going to use the word synergy. Sorry. Did I do that? So, that's awesome, man. As we end here, what are some patterns for developers to, one of the things I've noticed is when new things come, people just want to use them like there's no tomorrow. Let's look at the canonical example of today, the async await pattern in C# and VB.NET. It's being fully overused. And because it's so elegant and easy to use, I don't think developers are spending enough time understanding when maybe it's not really the right tool for the job.
Yep.
We're not going to go down that rabbit hole. Lucian Wilczek has a series of lectures that are going to be on Channel 9 with tips and tricks to explain to you this is what we meant. In the face of, we found out how it's actually being used and now we've learned more. So to be fair, it's really like, I guess this is the right way to use it as opposed to this is what we meant. At any rate, I would like to get from you guys a sense of what's the wrong way to use these collections? What are where the circumstances where don't do that?
Right. So
well, let me tell you one thing. I think in like with almost all the things in life, you only know when you're doing too much is when you actually stepped over the line. So you have to do things a lot in order to realize when is too much, right? And so I think mean, this goes back to my personal principle of stuff. I overuse stuff all the time to get a sense, what is the continuum where I can use the technology in order to know, like, okay, this doesn't feel right, but over here it's definitely too far. And so why is too far too far? Because once you understand what too far actually means, you can distill kind of like the principles where things make sense. Whenever there's something new, it's very hard to have the principles like all laid out for you. I mean, I think Stephen Tobe and Lucian did a really good job of presenting a talk, like what are the general performance costs for this whole thing, how should you think about async, and I think immutability is fairly new, especially, I mean, there are so many concerns you could have, like how, especially with types that are fairly used, right? The question is, yes, if someone uses them a lot and some other party doesn't, how do these two interact, for example? And so I think this is how I see this previews as well. I want to get it out to people. I really want people to overuse it to get the feedback. So I think right now I don't think there's a concern with could people overuse it. I think part of it would be overuse it up to a point, right? If you work in VS, that's probably not a good call, but but I mean, I think in general, like I think that's why previews are previews, right? You still want to churn the design.
Sure.
But
I've heard feedback from developers saying, hey, why did you use immutable list here? It's just a local variable. A list would have been just fine.
Yes.
And that's a fair point. On the other hand, kind of going along with overusing it, hey, why not? If we follow this pattern of write the most obvious code and optimize later, measure at the end, and the perf problems are never where you expected them to be. So will immutable collections overuse ever cause you a perf problem? Depending on your app, maybe not. And so if you prefer the syntax and the functional mindset that this affords you, I would say, yeah, by all means, use them. And then if you find out your app is too slow, measure your performance. If it happens to be that it's the one method where you were using immutable collections and you didn't need to, then just switch it out and use the immutable types and you're done, especially since that was a local variable case. That'll be an easy non-breaking change to make. We did have a couple of cases in the project system in Visual Studio where there were some very, very, very heavily hit methods that produced collections using immutable collections. But they didn't need the persistence characteristic. Nobody downstream, no consumer of these collections ever actually needed to efficiently mutate. They just wanted the assurance that it was a snapshot, that it would never change. And so we just changed them out. Our interfaces were already just exposed as read-only collection. So we just changed the implementation from immutable list to list of T, and you can use freezable collect. You could write your own little wrapper around that to guarantee it couldn't be cast back to the immutable one. But we just switched it to one without the persistence characteristic. Got our perf back up, and then the rest of our code base we still use the immutable collections all over the place, and we fixed our perf problem fairly easily.
Yeah, I mean, like this is another change that we did, right? We basically let our immutable concrete types implement the old mutable interfaces, but we did it in a read-only fashion. So basically we will throw whenever you would try to mutate. But the interesting thing is most people use the old things just for reading most of the time, at least that's what I found. So basically I think from a pattern perspective, and I think this is nothing new as well, is like if you basically code to an abstraction, you can change the implementation. So basically you can overuse like immutable today in your system. As soon as, as long as you basically agree on what the interfaces are, you still use the standard BCL interfaces. That still means if that doesn't work for you, you can change it back to a list of T or read-only, collection, depending on what you're actually doing there. And I think that's another general approach to solve this problem. Basically, being able in one part of your system to really toy around with it, use it, train yourself to use it, and get insight into whether you like it or not.
Great.
Excellent. Well, I mean, I know we didn't get to all the questions that the Niners had the first time we asked some other questions. I don't believe you answered the question around why is this all of a sudden important? Right? Because concurrency is something we've been freaking out about. I mean, I can remember 8 years ago, interviewing a bunch of folks, Chris Broom and others in a room. It never made the light of day on Channel 9, but the concurrency problem, remember? So I want to throw that out there because I don't believe we got that Niners question asked. So let's end it with this conversation. It's a great way to end this. Why did we begin this?
Yeah, I think it's a more or less general thing. Most of the computer science concepts we use today are not new, right? They're all 50s or 60s. But why is that? I think the interesting thing to observe is generally, like, if you come from a mathematical point of view, the interesting part here is that basically you have abstractions, you design these abstractions, and then you realize that it's really hard or expensive to implement those. On the other side, when you like also in the 60s or 70s, and people really wrote like assembler and stuff, so basically they didn't have any abstractions. They used whatever was the most efficient thing, and they would only ever add abstractions when they realized they can afford them. So you have these two very different camps. One like basically only removes abstractions when it's proven that they're not necessary. The other camp only adds them when they can actually afford them perf-wise. And so you will always find that, you know, even 10 years down the road or 15 years down the road, there will probably be more stuff that was probably invented then 100 years ago in some, you know, mathematician's like whiteboard. But now it actually becomes affordable or relevant or whatever, and then these guys, you know, show up again. And I think so this is a general trend where you see these two things, you know, getting married, you know, a lot. I think one thing to keep in mind though is that I think concurrency got more interest over the last 10, 15 years is basically, I think Herb Sutter phrased it well with like the free lunch is over. Mm-hmm. Like we can no longer say, well, next year you have a faster computer. Well, you will have a more powerful computer, but it will not run, you know, a single-threaded app faster because it will have more procs or more RAM. But in order to take advantage of this, you have to have, you know, a problem that is actually parallelizable in general. And so once you have more threads, well, naturally you want to have a way to, you know, deal with the side effects in a more meaningful way. Mm-hmm. And so I think async is not necessarily multi-threading, but async introduces like at least reentrancy in your app. So there's this, you know, desire to actually reason about your stuff in a meaningful way. So immutable collections give you one approach to that, which is snapshot semantics. But there are various other ways of doing it. I mean, there are locks, and you know, people used it with various different like degrees to success, I would say. How many locks do we take, for example?
In immutable collections, we take one, and that is when you're. We try really hard throughout the BCL to make enumeration of a collection free, no allocations at all. And so if you enumerate an I list of T versus it actually takes a couple of allocations to do that, but a list of T, we are able to use structs instead of objects and make that allocation free. But for an AVL tree, we do have to maintain some state about where you are. We have to maintain some stack, but when you're returning an IEnumerable, you can't use the threads call stack to do that. So we actually have a stack of T object that we use to track that as, but that would require an allocation for enumeration, which we really, really wanted to be free. So we actually have a cache. There's a static hidden implementation detail of every time we need a stack of T, we just reach into our, essentially a concurrent bag of stacks and say, hey, do we have a stack that we can reuse? And we use that, and so that we pull it out of the bag, associate it with this enumerator, and when the enumerator gets disposed, we put the stack back. And so by that, we're actually able to achieve allocation-free enumeration by reusing objects. It's not a concurrent bag, though. That actually isn't alloc-free itself, and so we use a stack of T, a mutable stack of T collection, and we lock around our access to push and pop out of that. That's the only lock that we use. It brings up an interesting one of those trade-offs, though. So we wanted alloc-free, so we got it. But one of the trade-offs we have is the danger of if you're using the enumerator as a struct, yet you, and it's kind of hard to get yourself in this situation. It's hard to do the wrong thing, which is where we want to be. But you can potentially dispose of the enumerator, then pass it, or have passed it to another method, and then dispose the enumerator. And then because we disposed it, we returned the stack. But because it's a struct, that a reference to that stack got passed to somebody else, and they may still be using the enumerator. Now you could be potentially corrupting other people because of multi-threading. Again, you had to break a few rules, you had to do some bad things, but it's all legal as far as the language. The compiler won't shout at you. But we decided, yeah, you have to write some pretty convoluted code to get yourself into the situation. And it does get you alloc-free enumeration, which is really important in some perf scenarios.
Yeah. Cool. Well, hey, thank you guys for coming on Channel 9 again.
Yep.
And, you know, it's nice to see these things continuing to evolve.
Yeah, keep the feedback coming.
Absolutely.
We're not done yet.
We're not done, yeah.
Right on. Cheers.
Thanks.
Thanks, guys.
Awesome.
Oh, how does this stop?